going to talk about solution concentration. Concentration is defined as the amount of solute in a solution. Some qualitative terms that we use are the term dilute. A solution that we would consider to not have that much solute in it, or concentrated, which would be a solution which we would consider to have a lot of solute in it. So some words that you've used are, weak, concentrated. This is a weak glass of Kool-Aid. This is a strong glass of Kool-Aid. Today, we're going to talk a little bit more quantitative. So those terms are really useful for relative stuff, but, we need to know specific numbers. We have several units that we use. So today we're going to focus on the ones that are related to moles. First unit we're going to look at is something called molarity. Molarity is defined as the number of moles of solute per liters of solution. So solution means, the whole solution, including both the solute and solvent. So you do have to be kind of cautious about that. It's not just per liters of water, even though we often kind of refer to it like it is. So you do have this as one of your concentration formulas on table T. And this says molarity equals moles of solute, liters of solution. Molarity actually is a unit indicated by a capital M, and it actually means moles per liter. So if we want to calculate the molarity of a solution that contains 4 moles of sodium hydroxide in 0.5 liters of solution, molarity equals moles per liter. We have 4 moles of our solute, 0.5 liters of solution. So we would simply do 4 moles over 0.5 liters. It's a nice time to review significant figures as well. So you're going to do your 4 divided by 0.5, which gives you 8. And you actually have more sig figs in your notes than I do up here. According to my numbers in here, I can only keep 2 sig figs. That should be 8.0. In the notes, you actually have 3 sig figs in each of these, so you'd actually be able to call this 8.00 molar. Sometimes you could have a 2-step problem that you might have to do if you're given, for example, we have 82.0 grams of calcium nitrate dissolved in 2.00 liters of solution. So since I have grams, I actually need to get this into moles. So I've got grams and liters so far. I'm going to first do a nice gram calculation. I've got 82 grams of calcium nitrate. Got to do a nice GFM for that. 164 grams, 1 mole. This is actually 3 sig figs, 0.500 moles. So to calculate my molarity, I'm going to plug my 0.500 moles in over my number of liters, which is 2.00. And when I divide these out, I get a 0.25 molar solution. Again, I don't really have my proper number of sig figs up here. They don't really agree with the packet, so I apologize for that. One more example, how many moles of NaNO3 are contained in 4 liters of a 1.3 molar solution? So in this case, molarity equals moles per liter. I'm plugging in 1.30 moles. I'm solving for, 1.30 molar. I'm solving for a number of moles. And this is a 5-liter solution. So this solution has 5.20 moles in it. It is important, I know it can be a little bit confusing, but it is important to keep in mind that capital M actually stands for moles per liter and not just moles. Very confusing concept, a little bit hard to get used to. So we have one more with some grams in it. We've got 10 grams of HNO3 dissolved in 500 milliliters of solution. So my 10 grams of HNO3, I'm going to have to turn that into moles. I've got a GFM of 170 grams for 1 mole. Which gives me 0.0588 moles. Now when I plug this into my molarity formula, since I have liters on the bottom, I have to be cautious because this is actually milliliters. So I'm going to bloop, bloop, bloop. This will actually be 0.0588 moles over 0.5 liters. Thus giving me a molarity of 0.188 molar. So you can go ahead and try these 3 questions, pause the video for a moment, and I'll put the work up. So question number 1, we've got 5 moles over 5 liters, which will create a 1 molar solution. Question number 2, we've got 4 molar solution. It has 2 moles in it. And I'm trying to calculate this. It actually come out in liters of solution. It's very close to your number of liters of water, so we kind of tend to use that interchangeably. You would need 0.5 liters or 500 mils. And last but not least, our KNO3 solution, 202 grams of KNO3, and we have a GFM of 101 gram per mole, so this is actually 2 moles. And we are going to put those 2 moles, actually 2.00 moles I should say, into 4 liters of water to give us a 0.5 molar solution. Another related idea is the idea of dilutions. So to dilute a solution basically means we're going to add water to it, thus reducing its concentration. Initial solution here, which is 1 liter of 10 molar NaCl. So if we were to take that solution and dilute it by putting it into a 2-liter beaker, so same solution, but we're just going to add water to, obviously adding another liter to it. One thing we didn't change. So from solution 1, if we have 1 liter of a 10 molar solution, so that means we have 10 moles 1 liter, we have 1 liter of that, we still have 10 moles of NaCl, okay? So this solution up here is 10 moles per liter, we have 1 liter of it, telling us we have 10 moles of NaCl. Now, what we actually did here was we added water to this. So now I have 2 liters of solution present. So this is going to change the number of moles per liter I have. I don't still have a 10 molar solution because I now have 10 moles of NaCl. But they're not dissolved in 1 liter of solution anymore. They're dissolved in 2 liters of solution, which is actually going to cut my molarity to 5 molar. So by doubling the volume, we actually half concentration. That's dilution. It makes sense. You added water, it's going to make it quote unquote weaker. So our first solution, like if we imagine, just looking kind of a generic particle view, we have some fairly crowded particles in that 10 molar solution. When we now go down to having only a 5 molar solution, we're really going to have far less crowded particles. We did not change the number of moles. We still have 10 moles of salt in each one of those. What we did change is the volume of solution. So we ended up seeing solution 1 is 10 moles per liter, or 10 molar NaCl. Solution 2, because of having twice as much water, is 5 moles per liter of NaCl. Even though they have the same amount of stuff in there, 5 molar one just has it distributed over more space. So we have a formula for this. This actually looks really similar to what's called your titration formula. And we don't specifically use this formula a ton, but it's a really nice, easy to use formula that's very relevant in a lot of areas in college. So I do like to make sure that we get some use out of it. So if we have a 150 milliliter solution, that's 0.35 molar, or I'm sorry, we're going to make one of those, and we had 4 molar acid. This is going to allow us to figure out how to do the solution. So we are starting with something that's 4 molar. We want it to be way, way, way lower molarity, okay? So our goal is to get a, so here, an M2 of 0.35 molar, and a V2, or an amount, so this is our volume right here, of 150 milliliters, starting from our initial molarity of 4 molar. Now, whether you call these 1 or 2, it doesn't matter, as long as the 0.35 and the 150 are grouped together. So in this equation, what's also nice is you don't have to change milliliters into liters. Molarity needs to be a molarity, but as long as you're consistent all the way through, you can actually put your volume, if your volume's in milliliters, you can leave it that way. So we're going to plug in our M1, which is 4 molar, times our V1. And then on the other side, we're going to have our M2 and our V2. I also want to add to this, I'm sorry, in your packet I really do have the proper number of sig figs. So really, there's another 0 here, another 0 here, that is going to increase our number of significant figures. And this is going to give us a V1, meaning the amount of 4 molar acid that we're going to use is going to be 13.1 milliliters. And we know this is milliliters, not liters, because that's milliliters. Those two just have to agree. They don't have to be changed into liters. I do dilutions a lot because we actually get 12 molar hydrochloric acid. So if I take 1.5 liters of 12 molar hydrochloric acid, and again, I'm going to add my zeros on there to keep my proper sig figs, consistent with the packet, 12.0. And I need to get this to a new volume of 2.00 liters. What will be the concentration of the acid when I'm done? So I've got a V1 of 1.5 liters, and an M1 of 12.0 molar, and a V2 of 2 liters. This happens to be in liters this time. That's fine. I can keep it that way. So M1 V1 equals M2 V2. M1 1.5 molar times 12.0 molar. Or I'm sorry, 1.5 liters. Equals 2.00 liters times V2. And that's going to give us a V2 of 9 molar. And that makes sense because I diluted this. I added some water to it. I do expect the molarity to go down. I didn't dilute it a ton though. I only really added about half a liter, so it shouldn't go down too much.